Okay, now I will start the lecture. Okay, please confirm me once that my voice is clearly audible and you are able to see the screen.
Yes, sir.
Okay, start. In last lecture, we have started the discussion related to the phase diagrams, and in previous lecture, we have completed what is the meaning of the phase diagram, and what are the applications of phase diagrams, and what are the different types of the phase diagrams, depending on the solubility of one metal into the another metal in the liquid state and in the solid state, and depending on that. Now here, as far as your syllabus is concerned, in your syllabus you are only having the binary alloys in your syllabus, and for that binary alloys we are having only four types of the phase diagrams. Out of that, first two we have completed the discussion, that is isomorphous system and layer type system, and then remaining two, these two types of systems we will discuss in this lecture. Now I will move towards the third type. Okay, third type of the phase diagram is eutectic systems. Now, these types of the diagrams are obtained for two metals which are having complete solubility in each other in the liquid state, but these two metals will be completely insoluble in each other in the solid state. For example, you can say that PBS, that is the lead and arsenic, then BICD, that is bismuth and cadmium, then THTI means thorium and titanium, then AUSI means gold and silicon. Now, this is the phase diagram, general phase diagram for any type of eutectic system. You can consider any example from these 3 to 4 examples which I have mentioned in this slide. Here you can clearly see that whenever that alloy is in liquid state, only one liquid will be there. That is, both metals are completely soluble in each other. And when you are cooling that alloy from liquid state to the solid state, at the end means at the room temperature, you are getting a mixture. In this mixture, you will get the two different solids. Here, layers of two different solids will be there present. Here in this diagram, it is represented by A plus B mixture, or it is also termed as the eutectic mixture, okay, which is often at the end. Now, this is the general diagram for eutectic system. Now, first of all, I will explain each and every point or all the terms which are involved in this diagram. And after that, we will go for the microstructural changes which are occurring in this eutectic system. Now, first you can see that clearly here. Here, this diagram is, here we have drawn this diagram by considering the elements or alloy of elements A and element B, and this point C is the melting point of element A, and this point G is the melting point of element B. Now, when you can see here, two inclined lines are present, line CE and line GE. Now, from this line, what this line indicates here, when in element A, amount of element B increases, then melting point of this alloy will goes on decreasing, and when in pure metal B, amount of element A increases, then its melting point will decrease continuously. Now, this point E is the intersection point of this C line and G line. This intersection point will be the, or this intersection point here I have marked it as E. This will be termed as the eutectic temperature, and this eutectic temperature will be the minimum melting point of that particular alloy. If you take any composition in throughout this diagram, any composition of these two elements A and B, this point E will be having the least melting point of that particular alloy, and this E will be termed as the eutectic temperature, and corresponding composition to this point E will be termed as eutectic composition, that is ZE. This ZE will indicate here eutectic composition. This point E will indicate the eutectic temperature, and this corresponding alloy will be termed as the eutectic alloy. Now, due to this eutectic alloy or this eutectic temperature point, this diagram is divided in two parts. I am highlighting this line here. This vertical line will divide this diagram. The portion which is present towards left hand side of this eutectic composition, it will be termed, all the alloys will be termed as hypoeutectic alloys, and all the alloys which will be present towards the right hand side of this particular this point E, it will be termed as hypereutectic alloys. From this point A to ZE, all the alloys will be hypoeutectic alloy, and from point ZE to point B, all the alloys will be hypereutectic alloys, and at exactly at point E, that is point ZE, that particular alloy will be eutectic alloy. Okay, in this way, this total diagram will be divided in the three portions by considering the different composition. The first composition will be either that alloy will be having hypoeutectic composition, or eutectic composition, or hypereutectic composition. Okay, now for these three portions you have to consider uh, three different three different alloys, and you have to explain the microstructural changes occurring during the cooling. This is the first curve. It will be explained in the next slide, that is cooling of an alloy, hypoeutectic alloy with Z% B, then cooling of an eutectic alloy with Zd% B, and cooling of an hypereutectic alloy with Z-% of B. Now, before going for actual microstructural changes for each of these curves, first of all, I will explain what are the liquidus line, what is this solidus line in this particular diagram. This line C, E, and G is the liquidus line. Above this line, all the metals or alloys will be in the liquid state. In this line C, D, E, F, G. C, D, E, F, G is the solidus line. Below this line, all the metals or alloys will be in the solid state only. Okay. This C is the melting point of element A, G is the melting point of element B. This CEG is the liquidus line. Above this, all the metals and alloys will be in liquid state. And C, D, E, F, G, this is the solidus line. Below this, all the metals and alloys will be in the solid state. Okay. Now, after this, we will go for the microstructural changes. Microstructural changes for first curve is for hypoeutectic alloy, then eutectic alloy, and hypereutectic alloy. We will move towards the next slide. Okay, this is the slide for the hypoeutectic alloys. Hypoeutectic alloy. This is for wait. Please first draw this diagram so that when I am explaining you the microstructural changes, you should be able to see that actual diagram and the microstructural changes also. Please draw this diagram for eutectic system with these three cooling curves. Sorry, with these three different alloys. That is the alloy with Z% of B, then alloy with Zd% of B, and alloy with Z-% of B. Please draw this diagram with three different alloys composition. Please draw it, and after completion, let me know. Okay. Now I will explain the microstructural changes which are occurring for here, and these microstructural changes will be for three different alloys. This is the first alloy. This is the first alloy. This is the hypoeutectic alloy with Z% B, and this is the second alloy. This will be your eutectic alloy with Ze% of B, and this is the hypereutectic alloy with Z-% of B. Please try to understand the curves which I am showing here. I am highlighting here. This is the hypoeutectic alloy. This second one is the eutectic alloy, and this third vertical line will be showing the hypereutectic alloy. And first, we will start with the explanation or microstructural changes which are occurring for this hypoeutectic alloy with Z% of B. Now here, from point 1 to 2, I will first explain here, and then I will move towards that actual diagram. Okay, from point 1 to 2. Okay, here I am moving my cursor here. From point 1 to 2, alloy will be in liquid state only from point 1 to 2. Whenever you are drawing the microstructural changes, you can draw microstructures for each stage. That is for 1 to 2. You have to show that for 1 to 2, and you can draw one arrow, and in front of that you can draw one circle, and in that you can show one liquid only. Okay, from 1 to 2, only liquid will be there. From this 1 to 2, only liquid will be there. Then when during the cooling process, when temperature falls below this point 2, when temperature falls below this point 2, then solidification process will start, and this solid means element A will start separating out from this liquid. Okay, element A will start separating out from the liquid, and the composition, sorry, the actual amount of the solid A will vary along this line CDE, and amount of liquid will vary along this liquidous line CE. Okay, means when temperature falls below 2, amount of solid will start increasing as element A will start separating out from the liquid, and this process will continue up to point 3. Means in this region 2 to 3, your alloy will consist of solid A and liquid. And when the temperature will reaches at point 3, this remaining liquid will get completely solidified into mixture of two solids, that is solid A and solid B, and this mixture of two solids will be termed as eutectic mixture. Now we will then, from point 3 to 4, no change will be there in the phases. Now we will move towards this diagram. Here from 1 to 2, only liquid is there. Then when temperature falls below point 2, then element A will start separating out. Okay, this is shown in this diagram. This is point diagram A will show the microstructural changes which are occurring from point 2 to 3. Means from the liquid, element A is separated here, and this element A will be termed as proeutectic A, or it is also known as free A or primary A. Why this is termed as proeutectic, free, or primary? Because this element this element A has been separated. This element A is separated here in this 2 to 3 region. Element A is separated before point 3. Means actual eutectic transformation process will occur at this line, this horizontal line, this DEF. Okay, at this line, when temperature reaches at this particular point D, this liquid will get transformed to the mixture of two solids. That is the eutectic transformation reaction. But this element A has been separated before the actual eutectic transformation. That's why this element A, which is separated before this point 3, it will be termed as proeutectic A. Okay, this diagram A will indicate the microstructure during in the region 2 to 3 liquid plus proeutectic A, or it is also termed as free or primary A also. And why it is termed as proeutectic A? Because it is separated before the actual eutectic transformation. This A microstructure changes are for region 2 to 3. Then this diagram B will indicate the microstructural changes which are occurring in the region 3 to 4. Now, whichever amount of liquid is there in this part A, this liquid will get transformed to the mixture of two solids, that is mixture of A and B. Here the name is given as eutectic mixture A plus B. This proeutectic A will remain as it is in the last stage also, and whichever amount of liquid is there, this total liquid will get transformed to the mixture of two solids, that is two elements A and B, and this mixture will be termed as the eutectic mixture. Okay, this is proeutectic A, and this liquid will get transformed to the mixture of two solids A and B. So these are the total microstructural changes occurring during the cooling of an hypoeutectic alloy with Z% of B. Okay, from 1 to 2, I will repeat it again. You can please, whichever diagram you have drawn, that phase diagram, please refer that diagram in that first cooling of hypoeutectic alloy with Z% B. From 1 to 2 region, alloy will be in the liquid state only, and when temperature falls below that point 2, solidification process will start, and that element A will start separating out from that liquid. This element A, which is separating out before actual eutectic transformation, will be termed as proeutectic free or primary element A. And these microstructural changes are shown in this diagram, which is highlighted by name A. Then whichever amount of liquid is present, this liquid, when temperature falls or reaches at point 3 or below that, this liquid will get transformed to the mixture of two solids which contains element A and element B. This mixture will be termed as eutectic mixture. And whichever transformation reaction is occurring, that is one liquid is producing two solids, this transformation reaction will be termed as eutectic reaction or eutectic transformation. So these are the microstructural changes. Please draw this diagram, and then I will explain the next curve or microstructural changes for the next alloy. Whether these microstructural changes explanation you have understood it completely, please let me know.
Yes, sir.
Okay, please draw this diagram. This diagram A is for region 2 to 3 and diagram B is for region 3 to 4. Please draw the diagram, and after completion of it, please let me know that you have finished the diagram. Then I will move towards the explanation of the next alloy. Okay. Can I move towards next point then?
Yes, sir.
Okay. Prajwal is there. Prajwal.
Yes, sir.
Okay. Are you drawing the diagrams?
Done, sir.
Okay, wait. I will take it back. Paras Mule. Are you there? Paras Mule. Are you there? Okay. Any other person? Samarth Chavan. Samarth Chavan. Are you listening to me? Roll number 15. Okay. Okay. Then we will move towards next slide. Okay. Now, the next explanation for next alloy we are considering is alloy having composition is ZE% of B, means actual eutectic composition, and that alloy will be termed as eutectic alloy. Now from this diagram, first I will explain the changes by marking here, and after that I will show you the actual microstructural changes. From this, we are considering this alloy cooling of an alloy having ZE% B, or it is also known as eutectic alloy because it is having exactly eutectic composition. Then from point 1 to E, alloy will be in liquid state only. From this point 1 to E, alloy will be in liquid state only. And when during the cooling, when temperature reaches at point E, now this total liquid will get transformed to mixture of two solids, that is solid A and solid B. This transformation is termed as eutectic transformation. And from point E to point 2, that your alloy will remain in the solid state only. From point 1 to E, only one liquid will be there, and from point E to 2, phase will be solid, but it will be having two different solids, that is solid A and B. Now, microstructural changes will be like this. From point 1 to E, only liquid will be there, and when temperature reaches at point E, eutectic transformation will occur, means whichever amount of liquid is there, this liquid will get transformed to mixture of two solids, that is A and B. Now here there will be difference in the morphology. That's why I have shown some inclined line and some horizontal lines. For example, you can say that some of the solids, suppose A will be shown by horizontal line, then B will be shown by that inclined line, like this. They will be having different morphology or different appearance. Okay, so this will be termed as the eutectic alloy. Only one transformation will be there, that is this liquid will get transformed to mixture of two different solids, and this transformation reaction is termed as eutectic transformation. Okay, please draw this diagram, and after completion of this diagram, you can put that in the chat box. And if you are having any query, please also you can mention that in the chat box, or you can ask me directly also. Please draw the diagram. Please give proper names also for that diagram. Please draw this third diagram. It is this is alloy for microstructural changes during solidification of hypereutectic alloy with Z dash percent of B. Just draw the diagram. I will explain it. Have you completed this diagram?
Yes, sir.
Okay. And I will start the explanation for this diagram. For your reference, you can use this diagram. Please keep the microstructures in front of you, and I will explain the diagram here. Now, here we are. I am going to explain now cooling for this particular alloy. That is the third alloy, cooling of an hypereutectic alloy. Why this is termed as hypereutectic alloy? Because it is having composition more than the eutectic composition. That is the its composition exceeds this point E. That's why it is hypereutectic alloy. Now, whenever you are cooling and hypereutectic, suppose a hypereutectic alloy from liquid state up to the solid state or room temperature, then following changes will occur. Then suppose first region will be, here I have marked the point 1, from point 1 to 2. From this point 1 to point 2, your alloy will be in the liquid state only. 1 to 2, when temperature falls in this region 1 to 2, whatever may be temperature, the phase will be only liquid. And when temperature drops below this point 2, then from this liquid the element B will start separating out. Element B will start separating out, and whichever element B will separate before this point 3, that element B will be termed as proeutectic B, free element B, or primary element B, because this is separating before actual eutectic transformation. That's why it is termed as proeutectic free or primary element B. Now in this region 2 to 3, your alloy will be in liquid plus solid state. Liquid plus this proeutectic element B. Then when temperature reaches at point 3, here eutectic transformation will occur. This liquid will get transformed to mixture of two solids. One liquid will give mixture of two solids, that is element A plus element B. Now throughout this region 3 to 4, here only solid phase will be there, and you will be having the mixture of element A and B, that is your eutectic mixture, and you will be having that proeutectic B, which has been already separated before point 3. Now these microstructural changes you can understand from this diagram also. From region 1 to 2 only liquid will be there. Then in region 2 to 3, this proeutectic B is separated here, means element B will get separated from that total liquid, means your microstructure will consist of liquid plus this proeutectic B. And this will be the microstructure in the region 2 to 3. This diagram A will represent the microstructure from region 2 to 3, and this diagram B will represent the microstructure in the region 3 to 4. Means whichever amount of liquid is present in diagram A, this liquid will get transformed to mixture of element A and B. This mixture is nothing but the eutectic mixture. Here both elements will be there, and whichever proeutectic B is there, it will remain as it is at the room temperature also. So this is the these are the microstructural changes which are occurring here whenever you are doing the cooling of a hypereutectic alloy. This will be the microstructural changes, and this is for the hypereutectic alloy. Okay, so in this way, this eutectic system is finished. In this, whenever this question is asked, you have to explain what is the meaning of eutectic system, and you have to mention there some examples, one or more examples you can mention there, and you have to draw the actual diagram. And you have to, first of all, you have to give the description of that diagram, that is which elements alloy you have considered, alloy for element A, B, then melting point of element A, melting point of element B, then which is the solidus line in that diagram, which is the liquidus line in that diagram. Then after that, what are the different regions, means which is the eutectic alloy, which is the hypoeutectic alloy, and which is the hypereutectic alloy. And depending on that three different alloys, you have to give the microstructural changes for three different alloys: hypoeutectic alloy, eutectic alloy, and hypereutectic alloy for the eutectic system. If you are have in this way, this eutectic system is completed. Now the next and last phase diagram will be phase diagram for partial eutectic system. Now this is the partial eutectic system. Now before actual starting this, I will explain what is the meaning of partial eutectic system. Here partial eutectic system is obtained for the for a alloy having two metals in which both the metals are completely soluble in the liquid state. Here you can see in this diagram only one liquid phase is there, or one liquid we are showing in this diagram, that is both metals are completely soluble in each other in the liquid state, but partially soluble in the solid state. Partially soluble, here instead of element A, I have mentioned here alpha, and here instead of element B, I have mentioned here beta. That I will explain here, but just try to understand what is the meaning of partial eutectic system. Both the elements will be completely soluble in each other in the liquid state, but and or you can say that, and partially soluble in the solid state. Means some amount of element, suppose you have considered alloy of element A and B, then uh, when temperature falls below the melting point temperature, then some amount of element B can dissolve in element A, and some amount of element A can dissolve in element B. That is termed as the partial solubility. Means element A can dissolve, some amount of element A can be dissolved in element B, and some amount of element B can be dissolved in the element A. Okay, this will be the concept of the partial solubility. Now what is this alpha and what is this beta, that I will explain, but try to understand some practical examples for this partial eutectic system. Here a very well known example from your practical life is the AgCu. AgCu means silver and copper's example is there. Silver and copper, these are partially soluble in each other in the solid state also. Means in liquid state they will be completely soluble in each other, and in the solid state some amount of copper may get dissolved in the silver, or some amount of silver may get dissolved in the copper. Few another examples are PbSN, that is lead and tin, then tin and bismuth, that is SnBi, then lead. PbSb, PbSb is nothing but lead, and Sb is the antimony. Pb is the lead and Sb is the antimony. CdZn is the cadmium and zinc, then aluminum and silicon. So these are the different alloys which shows the partial eutectic system of the phase diagram. Please draw this diagram, and after drawing this diagram I will explain you the different terms, that is what is the meaning of alpha, what is the meaning of beta, then what this curve or line HD will represent. Then this curve or line, here I will highlight this HD, then KF, like this different terms are there that I will explain it. First draw the diagram, and after completing the diagram, please put that in the chat box, and if you are having any query you can also put that. I will wait for 1 minute here, 1 or 2 minutes I will wait. Pawan Gowri is there, Pawan Gowri.
Yes, sir. Yes, sir.
Okay, please draw the whichever diagrams are there, please draw in your notebook, so that you will be able to remember the different terms and different structures and different examples also. Okay, if you have completed this diagram, I will start the explanation. Okay, now this is the general phase diagram for partial eutectic system. Now here we have considered this phase diagram for two elements, or you can say that alloy of element A and B. Now on this y-axis temperature will be there, and on x-axis weight percentage of element B will be there. Here at this point, or you can say that the origin point here, A will be 100% and B will be 0. And at the rightmost corner, this here B will be 100% and A will be 0. Then this point C, this point C will represent the melting point of element A, and this point G, this point G will represent the melting point of element B. Okay, these 2 points will indicate the melting points. Then after that, this line C, E, G. I will move this cursor here. C, E, G. This line will be termed as liquidus line. This C, E, G will be liquidus line. Above this line, your metals or alloy will be in the liquid state only. This line C, E, G. Now, this region or this line C, D, E, F, G. I will repeat it again. C, D, E, F, G. This line will be termed as solidus line. Below this line, all the metals or alloys will be in the solid state only. Now, after this liquidus line and solidus line, this C, E, G is liquidus line. This C, D, E, F, G is the solidus line. This is solidus line. Okay. Now, after this, what is the meaning of this alpha and what is the meaning of this beta, and what these two inclined line will indicate? Okay, this horizontal line DEF, it will show the point at which eutectic transformation is occurring. Okay, this is eutectic transformation line, this DEF. Okay, eutectic transformation will occur at this line. Now, what is the meaning of alpha? Alpha is nothing but solid solution of element B in element A. Please listen this carefully. What is the alpha and what is the beta? Alpha, as these elements are partially soluble in each other, this alpha will represent the solid solution of element B in element A. Means here element A will act as a parent metal and element B will act as the alloying element or solute. That will be termed as alpha, means solid solution of solid state solution, and it is solid state solution of element B in element A. Here A will be parent metal and B will act as the alloying element. That will be termed as alpha. Okay, and beta is the solid solution of element A in element B. Means here B will act as a parent metal, means as parent metal its percentage or its quantity or amount will be more, and element A will act as the alloying element or solute. Okay, this solid solution will be termed as beta solid solution. Okay, in short, you can say that this alpha and betas are solid solutions of element B in A and element A in B. This alpha is the solid solution of element B in element A, and this beta is solid solution of element A in element B. Okay, whenever alpha solid solution is there, means some amount of beta element is dissolved in element A. That will be termed as alpha solid solution. And beta solid solution means some amount of element A is dissolved in parent metal B. That will be termed as solid solution beta. Now, what this line HD, please go through this line HD and line KF. This is line KF, this is line HD. This line HD and line KF, these are termed as the solvus lines. Okay, solvus line. This is the solvus line. This DH and KF, these are the solvus lines, and what these lines indicates solubility of element. Now I will explain this HD line. Solubility of element B in element A from room temperature up to the higher temperatures or eutectic temperature point. This curve will indicate that solubility of element B in A at room temperature up to the eutectic temperature point. Okay, similarly this KF line, this is also a solvus line. It will represent the solubility of element A in element B at room temperature and solubility of element A in element B at higher temperatures or at the eutectic temperatures. Okay, so these are the solvus lines which will indicate the solubility of one metal into the another at a room temperature. At room temperature, solubility is indicated by point H, and point H and point K, and at eutectic temperatures, this solubility is indicated by point D and point F. These are the solvus lines, HD and KF. Okay, so this is the explanation for this partial eutectic system. Now, this diagram will be divided in the now here you have to, for showing the microstructural changes, you have to consider the different alloys in the eutectic system. We have considered three alloys depending on the nature of that diagram. Here also you have to consider different alloys. The first will be your eutectic alloy having exact eutectic composition. Then here, whenever alloy is having lesser composition, that is hypoeutectic alloy, here two different regions are there. Okay, this region where you are having alpha in that region, and here where you are having this alpha plus liquid, and directly you are getting the eutectic reaction or eutectic mixture. That will be another example that is shown in the next slide. That is this diagram, you have to divide it. This is for eutectic alloy. Then this, whichever region is there towards left hand side, that will be hypoeutectic region, and whichever region towards right hand side, it will be hypereutectic region. This hypoeutectic region again will be having different alloys, but two types will be there, which is having the first type of the nature, that is this curve will represent the microstructural changes. Okay, microstructural changes within this region before this point D will be similar. That's why we are considering one alloy in that region. Then microstructural changes in this region will be similar from this point D to E. That's why we are considering one alloy in this region. Then after this, again from this point E to F, we can consider one alloy here, and after this point F, we have to consider one alloy here. Means total five alloys you have to consider here, and for that five alloys, you have to take the do the explanation for the microstructural changes which are occurring whenever you are doing the cooling from the liquid state up to the room temperature. Now, this part we will try to understand in the next lecture. Okay, we will see that in the next lecture. Up to this, if you are having any difficulty, you can ask me. If you are having any difficulty, please reply. If you are having any difficulty in the eutectic system and the initial description for that partial eutectic system, you can ask me.
No, sir.
Okay. Okay, one more thing. Okay, one notice is there. I have shared the PDF file of the notes for this first chapter on your group. Whether you have received it?
Yes, sir.
Okay, any other person, please reply me. No, sir.
Yes, sir.
Rajwal, whether you have
Sir,
received it?
no. Yes, sir. We have received that. No answer was for doubts.
Okay, okay. I thought you didn't receive that notes. Okay, okay. Anyone is there? Roll number. Roll number. Who is this? 23. Roll number 23. Prithviraj Deshmukh.
Yes, sir.
Okay, you are understanding my lectures.
Yes. Yes, sir. Yes.
Okay, okay. Whether you have received that notes soft copy which I have sent it.
Yes, sir.
Okay, okay. Please go through that. If you are having any
Hmm.
difficulty, you can contact me. Okay, now
Yes.
we will stop here. In the next lecture, we will go through this partial eutectic system, and whichever may be there, microstructural changes are there. That microstructural changes for different types of the alloys. It may be eutectic or hypoeutectic or hypereutectic. That we will learn in the next lecture. Now I will stop here. Okay. Thank you.